Hello and welcome to the tutorial on advances in debating technologies. What this tutorial is about, argumentation and debating are really fundamental capabilities of human intelligence. They are essential for a wide range of human activities that involve reasoning, decision making, or persuasion, and are common to all human societies. Computational argumentation is defined as the application of computational methods for analyzing and synthesizing argumentation and human debate. This field has been rapidly evolving over the last few years. For example, as we see in the figure, the number of hits in Google Scholar for argument mining or argumentation mining is rapidly increasing over the years, with more than 500 hits last year and probably more than 600 this year. So this is a lively research discipline that gradually gains more and more attention from the computational linguistics and NLP communities. And this tutorial is focused on a subfield of computational argumentation referred to as debating technologies. And by debating technologies, we mean computational technologies that are developed directly to enhance, support, and engage with human debating. And more specifically in this tutorial, we will focus on a recent important milestone in this field, Project Debater, which is the first and so far only AI system that was shown to be able to participate in full live debate with an expert human debater in a meaningful manner. So in this tutorial, for the first time, we will share a holistic and detailed view of how Project Debater really works, and correspondingly we'll get an overview of a list of highly interesting and challenging problems in the field of computational argumentation. In other words, while we review Project Debater, we also review many of the interesting problems in computational argumentation and how solutions to these problems can be composed together into a single system that can debate humans. While doing so, we will also share some lessons learned from our experience while developing such a complex, large-scale NLP system. So here's the tutorial outline. We are now in the introduction section. Next, we will discuss the argument mining capabilities of Project Debater, namely how we can pinpoint relevant arguments within billions of sentences with very high precision. In part 3, we will talk about argument evaluation and analysis, and more specifically about how one can automatically identify the stance of an argument and the quality of an argument. In part 4, we will talk about modeling human dilemma, that is, how to formally capture and exploit the commonalities between the many different debates that humans are having. Then we will take a 10 minutes break, and after the break, in part 5, we will talk about listening comprehension and rebuttal. And while we'll discuss many challenging tasks in this tutorial, being able to generate an effective rebuttal, I believe, stands out as exceptionally challenging. So still a lot of room for improvement in this area. Afterwards, in section 6, we will discuss some basic NLP capabilities that we needed to develop as part of Project Debater, which are of potential interest in other contexts as well. In section 7, we will talk about how to put all the pieces together. Namely, after having all the underlying building blocks, how do we move from a collection of many individual arguments, rebuttal arguments, etc., to a single coherent and compelling narrative? And finally, in section 8, we will share a summary and some recent works that naturally emerge from the work on Okay, so let's start. So as you may know, in IBM research, we have an interesting tradition of grand challenges in artificial intelligence. Back in the 90s, IBM introduced Deep Blue that was able to defeat Garry Kasparov in chess. In 2011, IBM introduced Watson that defeated the all-time winners of the TV trivia game Jeopardy. And just a few days after this event, an email was sent to all the thousands of researchers of IBM across the globe, and myself included, asking us what the next grand challenge should be. And I was intrigued by that, so I offered my office mate at the time to brainstorm together, and this is what we did. We sat in the office in Tel Aviv and raised many different ideas. And towards the end of the hour, I suggested this notion of developing a machine that will be able to debate humans, and that this is how we will demonstrate the technology through a full live debate between this envisioned system and an expert human debater. And this sounded better than all the other ideas that we had up to that point, so we decided to submit that. The only guidance we got were to submit the proposals in a single slide, so the management will not be swamped with too many details, and we carefully followed these guidelines and submitted a single slide back in February 2011. This started a fairly long and thorough review process that lasted for a year, and eventually in 2012, this proposal was selected as the next grand challenge for IBM research. And we started to work a few months later with a small team that gradually expanded, and after nearly 7 years of work dedicated solely to this mission of developing a machine that can debate humans, we demonstrated the system for the first time in a public event in San Francisco during February last year. And it was a full live debate between this system, now being called Project Debater, and one of the legendary human debaters in the history of university debate competitions, Mr. Harish Natarajan. And perhaps interestingly, it was surprisingly reminiscent to the vision that we had on that single slide back in the office in Tel Aviv quite a few years. The debate held in front of a live audience of around 800 people, mainly journalists from all the top media outlets, and correspondingly it received massive media attention, around 2.1 billion social media impressions, millions of video views, and lots of press coverage. And in fact, there was a full documentary produced covering the journey of our team, and the short version of this documentary is already freely available on YouTube, so you're all welcome to watch that immediately after this tutorial. And what we are going to do next is to see just a few minutes out of the live debate we had in San Francisco last year. But before that, let me describe the premise. The debate starts with a motion that defines what we are debating about. In this case, it was whether we, that is the government, should subsidize preschool. And there are many considerations around how this motion is being selected, which I'm omitting here. I would just emphasize that obviously it is selected from a list of motions that were never included in the training data of the system. Project Debater is on side government, namely supporting the motion. Harish is on the opposition. And we have opening speeches of 4 minutes for each side, rebuttal speeches of 4 minutes for each side, and closing statements for 2 minutes per side. So all in all, pauses included, we are talking about between 20 to 25 minutes of a complex discussion between human and machine. Let us now see 3 minutes out of that. The full live debate is available on YouTube, but let us just see 3 minutes out of that, and after that start talking about how this system actually.
Greetings, Harish. I have heard you hold the world record in debate competition wins against humans, but I suspect you've never debated a machine. Welcome to the future. When we subsidize preschools and the like, we are making good use of government money because they carry benefits for society as a whole. For decades, research has demonstrated that high-quality preschool is one of the best investments of public dollars, resulting in children who fare better on tests and have more successful lives than those without the same access. Secondly, a few words about poverty. While I cannot experience poverty directly and have no complaints concerning my own standards of living, I still have the following to share. Regarding poverty, research clearly shows that a good preschool can help kids overcome the disadvantages often associated with poverty. The OECD has recommended that governments subsidize pre-primary education to boost performance in poorer areas.
Well, thank you very much, everybody. It's a pleasure to be here for this historic event. And it certainly was a pleasure to listen to Project Debater. There was a lot of information in that speech, and lots of facts and lots of figures. The problem, though, is the reality of subsidizing preschools is one which does not deal with the underlying problems in society. If you massively increase the number of people going to preschool, they're all going to be the ones going to the high-quality preschools. In a competitive environment at the age of 3 or 4, when you're learning that that other child is potentially better than you, when you realize you aren't necessarily as talented as someone else, that huge psychological damage for many children may mean that preschool is actively harmful.
Among other things, I think Mr. Natarajan suggested that preschools should not be subsidized because this will reduce their quality. I would like to offer a different view. I disagree with my opponent. Subsidizing preschools will have no negative effect on their quality. If anything, the opposite is true. One of many reasons is that subsidizing attracts more skilled and qualified people to the field, improving the quality of preschools for all. My opponent claimed that preschools are harmful. I believe my argument suggested that the benefits outweigh the potential disadvantages. I touched upon 3 issues: children, students, and crime. Specifically, I noted that preschool education improves children's development. In addition, I suggested that attending preschool helps students succeed. And a final point to consider is that preschool can prevent future crime. We should subsidize preschools. Thanks for your attention.
Okay, so our third question at this stage is how this system works. And the short answer is given in this slide, and I will take you through that in the next few minutes. And then we are actually going to dive deeper on many of these components in the following parts of this tutorial. And as you will see, we published many papers over the years, but each paper typically highlights only one aspect of the system. So this tutorial, to some extent, is an opportunity to connect the dots and understand the system in its entirety. So first, let us clarify the input and the output of the system. The input to the system is just the short phrase that represents the motion. For example, we should subsidize preschool. That's it. And later on, of course, also the speeches delivered by the opponent. And the output of the system are 3 fairly long speeches that are articulated via an expressive text-to-speech system that we developed as part of this project, but we're not going to describe this aspect in this tutorial. Now, the system has 2 major sources of information. The first is the LexisNexis corpus. This is a massive collection of around 400 million articles, or nearly 10 billion sentences, coming from thousands of different newspapers and journals. And as the debate starts, the system is using various argument mining capabilities to pinpoint within these billions of sentences short pieces of text that satisfy 3 criteria. They should be relevant to the debate, to the topic. They should be argumentative in nature, not just relevant. They should argue something about the topic. And finally, they should support our side of the debate. And these parts will be discussed in detail in part 2 and part 3 of the tutorial. Next, the system is using clustering and other techniques in order to glue these short pieces together into a coherent narrative, as will be discussed in part 6 and part 7 of the tutorial. The second major source of information for the system is a unique knowledge graph that we developed over the years, containing thousands of what we refer to as more principled argumentative elements that try to capture the commonalities between the many different debates that humans are having. And when the debate starts, the system is navigating, so to speak, in this knowledge graph, trying to find the most relevant principled arguments and use them in the debate in the right timing. This part will be discussed in more detail in part 4 of the tutorial, but just to make it a little bit more concrete, what we mean by a principled argument, imagine that we are debating whether or not to ban the sale of alcohol or whether or not to ban cosmetic surgeries. In both cases, the opposition may argue that if we ban something, we are at the risk of the emergence of a black market that by itself has a lot of negative consequences. So the black market argument is a principled argument that can be used almost as is in many different contexts, in many different debates. And one may naively assume that this is just a keyword matching thing. That is, that if we debate whether or not to ban something, we should expect the opposition to make the black market argument and prepare accordingly. But of course, this is not always the case. Imagine a debate about banning internet cookies. Probably we're not going to see the emergence of a black market of internet cookies as a result, or think of a debate about banning homework or a ban on advertising and so on. So in other words, to find the truly relevant principal arguments that the system need to develop, I would say, a more subtle understanding of the human language, and the way we approach that will be discussed in part 4 of this. Next, we need to talk about rebuttal, and we do that. We approach the problem of rebuttal first by using Watson's speech recognition capabilities almost out of the box to identify the words articulated by the opponent. But of course, to generate a meaningful rebuttal, we need to go beyond that and to understand the gist of the opponent's speech, and more specifically the main arguments or the main claims raised by the opposition. And to that end, we use an arsenal of techniques that typically rely on the same principle. First, we try to anticipate in advance which claims the opposition might use, and then listen in order to determine whether indeed the opposition was making these claims, and if so, respond accordingly. And this very challenging task will be discussed in more detail right after the break in part 5 of this. Finally, in some cases, we would like to expand the scope of arguments that the system is considering and using during the debate. Imagine, for example, a debate about the two-party system in the US. We would like somehow the system to be able to understand automatically that the alternative to the two-party system is the multi-party system, and consider including arguments discussing the multi-party system during the debate in the correct stance. And this aspect will be described as well in part 2 of this tutorial. So this concludes a high-level description of the entire system, and in the following parts we will discuss many of the underlying capabilities in more detail. And as mentioned, over the years we published many papers and importantly released many associated datasets that are all freely available through our project website. So you are very much encouraged to explore this page and download the data that you have interest in. And by that, we conclude part 1 of this tutorial, and let us move forward to part 2.
Hello and welcome to the second part of Advances in Debating Technologies tutorial, which will focus on argument mining. Argument mining is one of the central capabilities that were developed in Project Debater. Large portions of the speeches that are automatically generated by the system are composed of arguments that are automatically extracted from a massive text corpus by the argument mining component. The task of argument mining in the context of Project Debater is given a debate topic, extract relevant arguments from a massive corpus. The corpus we worked with in Project Debater contained billions of sentences, and clearly given a debate topic, only a tiny portion of the text within the corpus contained relevant arguments. In order to enable the system to hold a live debate with a top human debater, it was necessary to develop a very powerful argument mining solution. The requirements from this solution were very challenging. First of all, there is almost zero tolerance for errors. If the system brings an irrelevant argument, it will most probably lose the audience. Second, a good speech is composed of a diverse set of arguments that cover different aspects of the debate topic. So it is necessary that the argument mining solution will bring arguments that address the different aspects of the debate topic. And finally, the participants in a live debate need to be prepared to debate on almost any possible topic, and therefore the high performance of the argument mining solution needs to be achieved for a wide range of unseen topics. In this part of the tutorial, we will describe the argument mining solution that we developed in Project Debater, and we will explain how we coped with these challenging requirements. In order to be able to identify relevant arguments, the argument mining solution needs to be able to distinguish between argumentative and non-argumentative texts. This task is far from being trivial, as we can see in the following example. The motion in this example is blood donation should be mandatory. Here we see two sentences that are both related to blood donation. At a first glance, these two sentences look very similar. They share similar words and phrases like a study and statistics, 88% and 80%. But while the first sentence discusses the health benefits of blood donation, the second just mentions the high rate of students among blood donors. So despite their similar vocabulary, only the first sentence is argumentative, while the stance of the second sentence towards the topic is unclear, and we therefore would like the argument mining component to detect the first sentence and filter out the second. Here we see another example. This time the motion is, we should abandon Valentine's Day. Again, the two sentences are very similar from the vocabulary perspective, but only the first sentence is argumentative. According to the first sentence, many Canadians think that Valentine's Day is a waste of time and money. The second sentence just states that people think it's good to end a relationship before Valentine's Day to save money. So it's not exactly clear if the sentence is for or against the motion. As demonstrated in the examples, the differences between an argumentative and a non-argumentative text can be very delicate and require the system to have a deep understanding of natural language in order to capture such subtle nuances. Before we move forward to describe the argument mining solution, let's have a look at the argument types that the debater's system is designed to detect. The first type is claim, a concise statement that has a clear stance towards the motion. Another type is evidence, a single sentence that clearly supports or contests the motion and provides an indication for whether a relevant belief or a claim is true. We distinguish between two types of evidence. Evidence of type study that includes a quantitative analysis of data, and evidence of type expert that presents testimony by a relevant expert or authority. In order to better understand the final argument mining component of the debater's system, Let's first have a look at the early forms of the solution. These two papers, by Ran Levy et al. And Ruti et al., describe the early claim and evidence detection systems. In preceding works in the field of argument mining, the main focus was on detecting argumentative text segments within a document, while the question of the relevance of the arguments to a given topic was not addressed. These two works were the first to tackle the problem of topic-based argument mining, where the arguments are detected with respect to a given topic. At these early stages of the project, Wikipedia served as the system's corpus. The idea was to develop a separate classifier for each argument type using supervised learning. Given a topic, professional annotators identified relevant Wikipedia articles and then annotated their sentences with respect to the desired argument type, for example, whether a sentence is a claim or not. These manually annotated datasets were used to train logistic regression classifiers using handcrafted features. One of the main limitations of the early argument mining solution was its relatively low precision. In order to increase precision, two complementary directions were explored: increasing the size of annotated data and moving from linear models to deep neural networks. A significant increase in the size of annotated data was achieved by using weak supervision. The papers by Ran Levy et al. And Eyal Schnarch et al. Adopted the weak supervision approach in the context of topic-based argument mining. In order to better utilize the potential of the larger annotated data, the two studies used a deep neural network for learning from the weakly annotated data. Levy et al. Did it for claim detection, while Schnarch et al. Did it for evidence detection and combined the weak labels with manual labels. The weak supervision used in the two studies is based on the heuristic introduced in the paper by Ran Levy et al. From ACL 2017. The DNN model in both studies was BiLSTM with inner attention. The combination of larger training data and a powerful DNN architecture resulted in significant precision improvements. Despite the large precision improvements, it was necessary to further enhance the argument mining solution in order to reach the level required for a practical usage in a competitive live debate. The current argument mining solution is described in this paper by Endor et al. From AAAI 2020. The next slides are based on this study. A significant enhancement of the current solution compared to the previous ones is a result of the transition to a massive corpus which is 50 times larger than Wikipedia. This corpus contains 10 billion sentences from 400 million newspaper and journal articles provided by LexisNexis. The transition to such a large and diverse corpus increase the potential amount and diversity of the mined arguments. As for the classification model, we moved from BiLSTM to BERT, a pre-trained language model that achieves state-of-the-art results in various NLP tasks. Since it is impractical for runtime reasons to apply the classifier to all the 10 billion sentences in the corpus, it was necessary to design queries which, given a topic, will help the system focus on small regions of the corpus which are enriched with relevant arguments. The classifier is applied only to sentences from the query results. BERT is trained on a large amount of manually annotated data, which is collected using a novel iterative process. To better understand how this end-to-end argument mining solution works, let's have a closer look at the queries. We distinguish between two types of queries: sentence level and document level. In the document-level approach, the topic is usually used as a query and the results are full documents. In the sentence-level approach, the queries can be composed of additional components other than the topic, and the query results are sentences. This table summarizes the pros and cons of each approach. In the document-level approach, the query is useful only if the documents are highly controversial. Otherwise, the proportion of argumentative sentences within the document is expected to be small. This means that the document-level approach is effective mainly for highly controversial topics. The sentence-level approach is less sensitive to the level of topic controversiality and therefore can be effective for a wider set of topics. From the diversity point of view, document-level results are less diverse since they all originate from documents that focus on the topic. Another advantage of the sentence-level approach is that the queries can be designed to retrieve specific argument types. For all these reasons, we chose to use sentence-level queries. The main drawback of these queries is the small proportion of argumentative texts, and we will describe later how we overcome this problem when creating the labeled data. As we mentioned earlier, the aim of the queries is to focus on textual regions in the corpus that are enriched with relevant arguments. One of the reasons we chose sentence-level queries is that they allow us to search for arguments of a desired type. To understand how this is done, let's have a look at the following example. This query looks for arguments of type study evidence. It is composed of 4 elements: a word from a study lexicon, the word that, the topic, and a word from a sentiment lexicon. The study lexicon is composed of words and phrases associated with studies, such as study, research, finding, etc. Here is another example of a query that is targeted at detecting study evidence. All sentences with a number followed by the topic and the phrase from the connector lexicon will be among the query results. Now let's move to describe the new labeling paradigm that we developed in order to create a large and balanced dataset of manually annotated sentences. The aim of the new labeling paradigm is to create a large set of manually annotated data that is also balanced with respect to the amount of argumentative and non-argumentative sentences. For this purpose, it is necessary to find a way to overcome the rarity of positives, namely argumentative sentences, within the data. We start a process of collecting labeled data by selecting a small initial seed of labeled instances. This can be done, for example, by applying the document-level queries for highly controversial topics and annotating the resultant documents. For highly controversial topics, the proportion of positive sentences in the documents is expected to be relatively high, and therefore the resultant initial seed is expected to be relatively balanced. This initial data is used to train an initial classifier. The classifier is applied to the query results. The sentences which receive the highest score from the classifier are sent for annotation. The annotated examples are added to the labeled data, and the process continues until enough data was collected. The advantage of annotating the top-ranked sentences is twofold. First, since these sentences were scored by the model as having the highest chances of being positive, the proportion of positives within this population is relatively high. Thus, adding them to the annotated data may result in more balanced labeled data. In addition, the negative examples among the top-ranked candidates are the most painful errors of the classifier since they decrease the precision among the top candidates. adding them to the training data can help the classifier learn how to classify this type of challenging examples, which may result in precision improvements. The resultant dataset contains around 200,000 manually labeled sentences, where more than 33% of them are positives. This is the largest argument detection dataset, much larger than its counterparts, not only in terms of number of sentences, but also in terms of number of motions. The combination of high amount of labeled sentences and the diversity of motions had a crucial influence on the generalization capabilities of the system and enabled it to achieve extremely high performance on a wide range of unseen motions. In order to evaluate the performance of the end-to-end solution, given a model, we annotated for each of the 100 test motions the 40 top candidates. We then perform a macro average of the precision over the 100 test motions. The results are shown in the graph. The blue curve represents the best performing classifier, which is paired with the sentence's motion and motion as inputs. The red curve represents the baseline, which is based on the classifier from the study by Schnarch et al., a BILSTM where the topic in the input sentence is masked. We can see that for the leading model, the average precision among the top 40 candidates is 95%. Notice that this is an average over 100 unseen motions. This means that given an unseen topic, the argument mining system was able to pinpoint 40 arguments from a corpus of 10 billion sentences with almost perfect precision. The results shown here are for evidence, but similar results were obtained for claims. One of the reasons we chose sentence-level queries was diversity. We preferred the sentences to originate from a larger range of documents. In this curve, we analyzed the diversity of the retrieved sentences by measuring for each number of top candidates the number of documents they originate from, and average over the 100 test motions. We do the same for the number of journals. As the graph shows, the sentences indeed originate from a diverse set of documents and journals. In order to increase the scope of the extracted arguments and to expand the boundaries of discussion, we perform a debate topic expansion. This work is described in details in a paper by Ro'i Bar Chaim et al. From ACL 2019. The idea is to find, for a given debate topic, related topics such as generalization, specializations, and alternatives. Let's have a look at the following examples. Suppose that the topic is homeopathy. Then arguments in favor of alternative medicine can also be relevant arguments in favor of homeopathy. Similarly, for specializations, and evidence about the harmful results of gender pay gaps can be used for contesting gender inequality. For alternatives, the stance is reversed. An argument criticizing the two-party system can be used in a debate to support the multi-party system. The debate topic expansion method is composed of 3 steps. In the first step, expansion candidates are extracted from a large corpus using a set of predefined patterns. Each expansion type makes use of a different type of corpus and patterns. For example, in many cases, alternatives will tend to appear in a pattern X versus Y. So this pattern is used to detect initial candidates for alternatives. In the second step, we apply a set of filters to the extraction results. Finally, supervised classification is used to identify good expansions amongst the candidates. Before we move on to describe related work, let's summarize the parts describing the argument mining component of the debater system. We present a first sentence-level end-to-end argument mining solution. We introduce a new labeling paradigm for coping with skewed label distribution, and this paradigm enables us to generate a large and balanced argument classification data. We use this data to train the powerful BERT model and gain significant improvements compared to previous models. We achieve high precision, the system achieves high precision on a wide range of topics. And we also use topic expansion in order to increase the argument's scope. We mentioned earlier two approaches for querying a heterogeneous corpus in the context of topic-based argument mining: sentence level and document level. While we adopted the sentence level approach in Project Debater, recent studies tackled the problem using the document level approach. In most of these studies, the retrieval was performed using Google search engine, where the topic serves as a query, and the top Google retrieved web pages are the documents from which the arguments are extracted. The largest document-based argument detection dataset is the UKP corpus, which was published by Stab et al. In EMNLP 2018. As we mentioned earlier, the document-level approach is more suitable for highly controversial topics. Indeed, this dataset is composed of only 8 topics, all of which are highly controversial. Stab et al. Used BiLSTM to learn an argument classifier from this corpus. In a later work, From et al. Achieved nice classification improvements by learning with BERT and adding topic information from external sources to the input data. In our argument mining solution, we use the sentence level classifier for determining whether a sentence is a relevant argument. Another approach is based on token level classifiers, where the tokens are classified into beginning, inside or outside an argument unit. In this example, the words nuclear and eat are labeled as beginning, bat is outside, and the other tokens are inside. The largest dataset in this context was recently published by Trotman et al. The main advantage of this approach is that it enables to handle sentences that refer to more than one aspect of the topic or contain more than one stance, as demonstrated in the example. The main drawbacks are the more demanding annotation process and the lower precision of the resultant classifiers. Argument mining has recently become a hot research topic, as reflected by the increasing amount of papers published in top NLP conferences, dedicated workshops, and even tutorials. Here are 3 recent surveys that explore the methods that establish the foundations for argument mining and review the recent advances in the field. I would like to thank you for joining the second part of the tutorial Advances in Debating Technologies. I hope you enjoyed it and hope to see you in the next parts. Bye-bye.
Hello and welcome to the third part of the tutorial on debating technologies. The previous section discussed argument mining. Here we discuss the evaluation and analysis of extracted arguments. We will focus on 2 tasks: stance classification and argument quality. Let's start with stance classification. The stance classification work presented here is mostly based on the following 5 papers from our group, led by Orit Toledo-Ronen, Charles Yoakim, and myself. How do we use argument stance in Project Debater? First, we must select for our speeches only arguments that support our side. Identifying arguments supporting the opposite stance is useful for rebuttal, as Jonathan will discuss in section 5 of the tutorial. Precision must be very high, since we really don't want to include any arguments supporting our opponent in the speech. That would be really embarrassing. But coverage should also be high because we don't want to filter out many good arguments just because we are not sure about the stance. Finally, like the rest of Project Debater components, it should work on unseen topics. The stance classification component in Project Debater has evolved over the years. In the early stages of the project, we only had a few hundred to a few thousands of arguments manually identified in Wikipedia articles. Many of these arguments were quite challenging from a stance classification perspective. And remember that we needed stance classification to work on unseen topics in a robust fashion. For these reasons, we relied less on the labeled training data and instead invested a lot of effort in developing external knowledge sources. Machine learning was employed to combine these knowledge-based features. Later on, we switched to training on arguments automatically extracted by the argument mining component from the much larger LexisNexis corpus. This resulted in a larger and simpler dataset for training in the order of 10,000s of examples. In parallel, there's been a great progress of deep learning methods for NLP. Therefore, we developed a hybrid approach combining our knowledge-based stance classification with a neural net. This version was used in the live debate of 2019. The current implementation of the stance engine is based on pre-trained BERT, fine-tuned on even a larger dataset with nearly 400,000 arguments. Next, we will describe each of these versions in more detail, starting with the knowledge-based approach. Let's look at an example of claim stance classification. The topic is, we should embrace the free market, and the claim is, government intervention is important for safeguarding against monopoly formation. Is it pro or con? What are the inferences that we need to make to determine the stance? We can decompose the problem as follows. First, identify the sentiment targets of the topic and the claim. Next, identify the sentiment towards these targets. We can see that the topic is positive about the free market, and the claim is positive about government intervention. We also need to identify the relation between the targets. Supporting government intervention implies opposing the free market, so we say that these targets are contrastive. If the stance towards one target implies the same stance towards the other target, we say they are consistent. Finally, we can compute the stance. Negative sentiment and contrastive targets flip the polarity. Here we have two positive sentiments and a contrastive relation. One flip in total, so the stance is con. We created a dataset of about 2,400 claims for 55 topics, which were annotated for these subtasks. Next, we discuss the implementation of each of these subcomponents. Let's start with target extraction. We trained a logistic regression classifier on syntactic, semantic, and sentiment features. The classifier was applied to candidate phrases, and the highest scoring candidate was selected. For targeted sentiment analysis, we identify positive and negative sentiment terms. Here, important and safeguarding are positive, while monopoly is negative. They are weighted based on their distance from the target. We also detect against as a sentiment shifter, reversing the polarity of monopoly, as you can see. We developed several lexicons for sentiment analysis. A large-scale sentiment lexicon of bigrams and unigrams obtained by training a classifier on an initial word-level lexicon. Automatically learned lexicons for sentiment composition. For example, the word treat is a negative to positive reverser. Treating something negative like cancer is positive. Powerful is a propagator. It propagates the negative sentiment to the phrase level, for example, powerful adversary. We also developed a large-scale sentiment lexicon of idioms, which were annotated via crowdsourcing, and you can see here a few examples. Under fire is negative, and over the moon is positive. These knowledge resources that we developed are being integrated into IBM's Watson Natural Language Understanding. Here you can see that it correctly identifies the sentiment of the idiom 2 thumbs up. If I change thumbs to fingers, the sentiment would be neutral. The last subcomponent is relation classification. How do we know that free market and government intervention are contrastive? We developed a random forest classifier which makes use of lexical semantic features indicated similarity and contrast, such as word-net relations, word-to-vec, and polarity-inducing LSA. In addition, we performed pattern-based relation mining from query logs. For example, if we see a query like free market versus government intervention, it is an indication of contrastive relation. Next, I want to describe a different approach that does not rely on sentiment. Actually, it does not rely on the content of the argument at all. Consider the following expert opinion. Is it for or against atheism? As you can see, this is a complex argument, not only for machines but also for humans. But what if I told you that this text is by Richard Dawkins? As you probably know, Dawkins is a famous atheist, so this argument is likely to be pro-atheism. And we can learn that Dawkins is an atheist by looking at Wikipedia. Wikipedia's categories contain valuable information about people's stance. For example, we can see that Dawkins is an English atheist, a critic of creationism, a feminist, and so on. Based on Wikipedia categories, we built a large-scale expert stance graph. Starting with a list of controversial topics, we automatically extracted candidate pro and con categories which were manually annotated for stance. All persons or experts in a category inherit its stance towards the topic. We ended up with more than 100,000 expert stances towards 114 topics. We also developed rule-based classification of category names for topics that are not in the graph. The stance classification implementation that we actually used in the live debate of 2019 followed the decomposition I previously described. However, some of its components were simplified. The argument mining component was guaranteed to extract only arguments that contain the debate concept, which greatly simplified the detection of the sentiment target. The identification of contrastive relations was based on rule-based detection of contrastive expressions, like the word alternative in the example. The alternative to fossil fuel are more expensive. The detection of the sentiment towards the target remained a challenging task. We used two sentiment analyzers, one based on our knowledge-based approach. The other is a neural net GRU with attention layer that was enhanced with token and sentence level knowledge-based features. For claims, we only used the deep neural network. For evidence, which are more complex, the knowledge-based and the DNN analyzers had to agree on the stance, otherwise we did not make a prediction. We further analyzed the internal structure of evidence arguments using rule-based methods. First, we aim to extract the main claim embedded within the evidence and send only this part to sentiment analysis. Second, we aim to detect the stance of the evidence towards the embedded claim and reverse the polarity if needed. The overall performance we obtained was very high, 95% accuracy for claims and 90 to 91% for evidence, and when making prediction for 90% of the arguments. And this was for unseen debate topics. After the live debate, we upgraded stance classification implementation to use BERT. We performed 2 phases of fine-tuning over the pre-trained BERT. First, we trained on arguments that were automatically extracted. This dataset was automatically augmented by using consistent and contrastive expansions from our work on debate topic expansion, which was described by Liat in the previous section. In the second phase, we continued the training using about 26,000 human contributed arguments. This classifier achieves high accuracy of around 92% on the arguments composed by humans. To conclude this part, I would like to mention some related work on stance classification. Stance classification has been applied to various types of data, including congressional floor debates, debating forums, public comments on proposed regulations, student essays, and argument components. Many different classification methods has been applied to this problem, including rule-based methods, feature-based machine learning, and various deep learning architectures. Content-based features such as sentiment and n-grams were extracted from the text itself. In addition, many of the works take advantage of contextual information, such as agreement or disagreement between posts or speeches, author identity, conversation structure, and discourse structure. Collective classifications that takes advantage of both content-based and contextual features was also shown to help. Finally, there have been a few shared tasks for stance classification, which were quite popular. In SEMEVAL 2016, Mohammed et al. Introduced the task of detecting sentiment of tweets towards a target entity. Stance classification was also a subtask of the rumor-eval shared task in SEMEVAL 2017 and 2019. The goal was to classify tweets in a conversation discussing a rumor into 4 categories: supporting, denying, querying, or commenting. Let's move on to the task of evaluating argument quality. This part is mostly based on the following 3 papers from Project Debater, led by Martin Gleis, Asaf Toledo, and Shai Gretz. Argument quality was introduced to Project Debater in the context of evidence convincingness. The evidence detection component in Project Debater aims to detect evidence in input sentences. This is a binary classification problem. The classifier score can be used to rank the sentences based on their likelihood of being a valid evidence. This ranking would prefer the most easily identifiable evidence. not necessarily the best evidence or the most convincing one. Therefore, we developed a separate component that aims to re-rank the extracted evidence according to their convincingness. Let's look at the following example. The topic here is the use of AI should be abandoned, and we have a pair of evidence. The first one is about a poll in China where 53% of the people agreed that AI will create new jobs. The second one says that the Wall Street Journal reported that evidence shows that AI will lead to more wealth, cheaper goods, greater spending power, and more jobs. So, which one is more convincing? There are several reasons to prefer the second evidence. The Wall Street Journal is a reputable source, and relying on evidence seems more convincing than relying on poll results, especially when the majority was only 53%. Indeed, our convincingness model preferred the second evidence, while the evidence detection model gave a higher score to the first evidence. This illustrates the significance of the convincingness module. Convincingness is one way to define argument quality. We will discuss this further later on. In order to train an argument quality model, we need training data. There are two approaches for annotating argument quality: pointwise annotation and pairwise annotation. In pointwise annotation, we are presented with a single argument and we need to assess its quality. For example, by answering a binary question such as, would you recommend a friend to use this argument in a debate? Or alternatively, rate the quality of the argument on a scale of 1 to 5. The problem with this approach is that it is often difficult to make such an assessment without a reference point. Different people may have different scales, leading to inconsistent annotations. In pairwise quality annotation, we are presented with a pair of arguments and need to choose which one we prefer. This annotation task is much easier because the assessment is relative and we can expect better agreement. However, this approach requires a quadratic number of annotations since we need to compare each pairs of arguments for exhaustive annotation. As can be understood from the previous slide, developing a large-scale, high-quality dataset on argument quality is one of the main challenges in argument quality research, and we addressed it in a series of works. Glaze et al., in their ACL paper from last year, developed a dataset for evidence convincingness using pairwise annotation. About 5,700 pairs were annotated for 70 topics. The evidence sentences were taken from Wikipedia. Toledo et al., in their paper from EMNLP last year, developed an argument quality dataset for arguments collected from large audiences. The dataset contains 6,300 pointwise annotations for 11 topics. A large number of crowd annotators, between 15 to 17, annotated each argument with a binary label, and quality score was computed as the fraction of positive annotations. After applying various cleansing methods to ensure the high quality of the dataset has 5,300 arguments with pointwise annotation. The dataset also contains 14,000 pairwise annotations, 9,100 after cleansing. They show good agreement between pointwise and pairwise annotations, especially when the pointwise score differences are large. Finally, Gretz et al., in their AAAI paper from this year, continued the work of Toledo et al. They developed the largest argument quality dataset to date, comprising over 30,000 arguments for 71 topics, with pointwise quality annotations. They compared two methods for inferring quality scores from the binary labels assigned by the crowd annotators, weighted average, and maze probability. The details are given in the paper. Here are the experimental results reported by Gretz et al. On the large dataset of 30,000 arguments. The dataset was split by topics into train, dev, and test sets, and the task was predicting the argument quality score. The evaluation measures were Pearson correlation and Spearman correlation with the gold quality scores for each of the methods used to derive these scores from the binary labels, weighted average and maze probability. Different methods were compared, and as you can see, the best performing one is fine-tuned BERT, adapted for regression, where the input contains both the argument and the topic. Next, I would like to mention some related works on argument quality. Havernal and Gurevich, in their ACL 2016 paper, have previously addressed argument convincingness. They define two tasks: giving a pair of arguments which one is more convincing, and ranking a set of arguments according to their convincingness. They worked on arguments from a debate portal for which they collected 16,000 pairwise annotations. From these annotations, they derived quality ranking for about 1,000 arguments. They reported experimental results using SVM and BiLSTM. In a follow-up work, Simpson and Gurevich improved the results on argument convincingness by using Gaussian Process Preference Learning, or GPPL. They show that GPPL is particularly helpful for small, noisy datasets and in an active learning setup. Moving on to a more theoretical work on argument quality by Faxmuth et al. As you can see, this work from EACL 2017 involved several research groups working on computational argumentation. It made several contributions: a survey on argumentation quality research, a taxonomy of major argumentation quality dimensions, and a corpus annotated based on the proposed taxonomy. Here you can see the resulting taxonomy. I will not get into the details, but the main dimensions of argument quality according to this taxonomy are logical quality, the cogency of the argument; rhetoric quality, its persuasive effect; and the dialectical quality, its contribution to the discourse. The last work I would like to mention is by Ginap et al. From ACL this year. This work addresses the quadratic complexity of pairwise annotations. They propose a sampling strategy for saving up to 93% of the comparisons in pairwise annotations, and a model for deriving scalar scores from pairwise annotations. They also introduce a new argument quality corpus with about 1,300 arguments annotated according to the dimensions I mentioned in the previous slide: rhetoric, logical, and dialectical. The pair argument scores are inferred from 40,000 pairwise annotations. And with that, we conclude this part of the tutorial. Thank you for watching.
Hello, and welcome to the fourth part of the Advances in Debating Technologies tutorial, which is about principled arguments. As a motivating example, let's think about what argument mining misses. Consider the motion we should increase the use of telemedicine, and the claim people always worry about new technologies, but they are the basis for mankind's advancement and prosperity. This kind of claim does not mention telemedicine explicitly. It touches upon a fundamental aspect of the debate, that of the fear of new technologies. It attempts to frame the debate to discuss this aspect of it, and it is common to many debates about technologies, but not all of them. So it could be used when we're discussing social media, the sphere of new technologies, when we're talking about autonomous cars, but maybe it's less relevant when we're talking about green technology, for example. And I should mention that the first point that does not mention telemedicine explicitly, it's a problem for us because we're doing sentence level queries. Okay, so how do we address this absence, this myth? A working hypothesis is that principled arguments, which are recurring in debates, can be written independently of any specific motion. Because they are recurring arguments, we can write them in advance. We can create a knowledge base of texts, these principled arguments and adjoining texts, such that when presented with a new motion, one we have not seen before, there will usually be relevant texts within this knowledge base that can be used in the debate about this novel topic. Let's see what are some advantages of such handcrafted text. So first of all, it allows us to solve the problem that we've mentioned. It allows us to author arguments discussing the principles underlying the motion. Also, as we've mentioned, such text can frame the debate in a certain way. We can select ones which will frame the debate in a way which is favorable to us. We can ensure that the texts are well written. And we can also supplement argumentative texts, which we can find with argument mining, with non-argumentative ones, such as jokes. For example, if we have this common issue of new technologies, maybe we can have a joke about new technologies. Also, the relations among the texts are clear because they are written in advance, so we can also annotate the text for the relations that exist among them. But the challenge is that when we're given a novel motion, to determine which texts are relevant for it, which ones we can actually use within this knowledge base. So how do we address this problem? How did we do it? We defined the classes of recurring debate themes or commonplace themes or principled themes. And we defined also in parallel a typology of texts like claims and evidence and speech openings, proactive claim, quotes, all kinds of texts. And for each class, we aimed to author texts of each type and annotate them as such, and also the relations among them as we discussed. Once we have this knowledge base, we wanted to develop a mechanism that, given a novel topic, determines which classes are relevant. And once we determine which classes are relevant, we can suggest texts from these matched classes to the debate construction component to be added to the speech. Okay, so let's talk about this in a bit more detail. What are the classes of principled argument? So one such class is the one we discussed earlier, the one about new technologies. So we define the class technology. And on the one hand, we define, for example, claims that are relevant for motions of this class. So for example, a proclaim could be that technology makes life better for many people. It can also have placeholders for the specific topic that we're discussing. On the other hand, we have to annotate the motions which belong to this class. So for example, we should subsidize electric cars, we should further exploit genetic engineering, we should adopt cryptocurrency, or one of the motions we've seen in the earlier slides. And we do this and define a set of such corpus, such classes. And for each such class, we write on the one hand the relevant text, and on the other we map motions to them. This defines our knowledge base and our training data. Our modeling goals in doing this is to define the set of principled arguments which have the following properties. First of all, they are coherent. People can easily decide if an argument is relevant for a motion. So when presented with this class of new technologies and a motion, people can easily decide whether the motion belongs to this class, whether arguments from this class are relevant. And if humans can do it, we have hope that the computer can do it as well. Second, we want this to be non-trivial, a non-trivial modeling. We don't want the claims to be very general so that they are applicable for every motion. We don't want them to be very specific, to be specific to one motion. And also, we do not want this to simply be a partition. This is often done in motion datasets, where motions are labeled as being about economy or technology, but we want to capture an aspect of the motion, or the various aspects of the motion, and not some general label. We want good coverage within this knowledge base. We want that most motions will belong to at least one class. We want the text to be real-world text, text that people would actually use in a debate, and not some artificial texts that are coherent and maybe non-trivial, but are not really used, which would be strange if the system uses it in a debate. And finally, as we've discussed at the first point, we want them to be computer-friendly. We want the classes to be such that we can automatically match them with good accuracy and with good coverage to novel motion. So how do we go about constructing these classes? We defined some 50 classes of this kind. We defined them first in the context of 100 motions. This gave us the idea of what are the recurring themes. But once we had that, we mapped nearly 700 motions to these 50 classes. And we exhaustively annotated all pairs of motions and classes. And for example, the classes that we have are listed on the right. So we have classes like adolescents' rights, animal rights, big government, black market. And for each class, you can see a claim that kind of supports the theme and opposes it, and also the number of motions that exist in the class from among these 689 motions. Okay, so now I want to try and convince you that we've actually achieved our modeling goals. So the first one was coherency, that people can easily decide if an argument is relevant for a motion. To do this, we sampled pairs of motions and copas, and from each copa we took an argument. So we had pairs of motions and arguments, and we showed them to crowd annotators. For example, the topic might be, we should ban homeopathy, and the claim might be, homeopathy is considered offensive by various religious groups. Here we've used a placeholder for the specific topic. So annotating such pairs, we could compare them to our ground truth and see if people agree with each other and if they agree with the ground truth. Well, we've seen that the Cohen's kappa agreement between the majority vote of the crowd annotators and the ground truth was 0.76, and the average inter-annotator kappa was 0.6. Both are fairly high values for these kind of tests. So I hope this convinces you that our ground truth, our matching of the kappas and motions, but as a byproduct, the definition of the kappas themselves are indeed coherent. The next two properties that we've discussed above are non-triviality and good coverage. So you can see on the graph on the right, for each class, the number of motions in it. So you can see, or let me tell you because it's difficult to see from the graph, that 87% of the motions belong to at least one copa. So it's good coverage. On average, we have 2 copas per motion. We have a maximum of 6 copas per motion. On average, a copa intersects with 12 others. And when 2 copas intersect, this intersection includes, on average, 20% of the motions in the class. So I hope this convinces you that we're actually modeling aspects of motions. We're not partitioning the motions, and by and large, we don't have classes which are very specific to a single motion or are very general such that they are appropriate for any motion. Okay, the next point that I want to convince you is that the modeling captures real-world text. To do this, we resorted to a dataset of 184 debate speeches from work by Shachar Milkin and others from our group. These are speeches made by professional debaters who were completely unaware of our COPA effort. We showed crowd annotators the entire speech and asked them whether COPA claims from matching COPAs are indeed made in this speech. And you can see the results below. For 87% of the speeches, at least one of the COPA claims was mentioned in the speech according to the annotators, usually implicitly. And for 66% of the pairs of a speech and a claim, the annotators say that they match. So this number, this 66%, I think it convinces that the COPA claims are on the one hand commonplace, they're indeed often made, but they're not trivial. They're not the kind of claims you can always make because in 34% of the cases they were not made. Finally, our last modeling goal was that the modeling would be computer friendly in the sense that computers can actually match motions to copas. We tried various classifiers and also an ensemble of them. Our greatest success was logistic regression, but maybe more modern methods today can achieve even better results. We examined the performance in a leave one motion out analysis, and you can see the results in the graph on the right. For example, with logistic regression, for a coverage of 0.5, that is, for half the motions, the logistic regression classifier suggests at least one class. The precision is 0.86. The precision is 1. The top motion is indeed the correct one. Okay, so we've seen that it's computer friendly. Maybe it's computer friendly because it's very easy, and we could have done better. So consider the class black market, and consider two motions which belong to this class. We should legalize cannabis, and we should ban sex work. This might lead you to suspect that matching emotions to the black market class is easy. We can simply look at the action, and if we see legalize or ban, we know that the black market is relevant. But this is actually not the case. So for example, consider the motion we should ban internet cookies, where it's not relevant, or the motion we should legalize polygamy, which at least on the face of it is not a relevant motion. So to summarize, we defined these classes of principled arguments, collections of texts based around a recurring debate theme. We manually annotated a huge number of motion copper pairs, 689 motions times 50 classes. We verified that this annotation has the desired properties, and if you're convinced that this is indeed the case, we've achieved something which is, I think, quite impressive, an explicit modeling of recurring arguments. This is something that professional debaters, I think, always have an intuition that it exists, but as far as we know, was never explicitly done. We trained the classifier to determine whether a motion copper pair is a match, so that when we're given a novel motion, we can go over all coppers and determine which of them match, and from those which match, we can use texts in the actual speech. So far, we've focused on arguments, but this is, as I've mentioned in the very beginning, it's not the only kind of texts we have in these classes. So for example, consider again the debate we should increase the use of telemedicine. So in the actual speech that was generated, the opening came from this knowledge base of corpus, and it starts by saying we're discussing today the merits of technology, its importance to mankind's ongoing advancement and prosperity, and so on. Then it lists a couple of claims, which is similar to the kind of things we've seen in the previous slides. For example, the use of telemedicine is reliable, where you have a placeholder for the topic telemedicine. Then we have many arguments coming from the argument mining. And then towards the end of the speech, we say, in today's debate, you're likely to see the other side express concerns about new technologies, their reliability, their track record, and so on, and so forth. So this again comes from the knowledge base, from the corpus, and you're seeing that we're trying to frame the debate in a proactive manner to be about new technologies. So what kind of text do we have other than claims and evidence? We also have openings, as we've seen, conclusions, as we've seen, proactive arguments, but also quotes, humor, closing words, some canonical examples. For example, the probation is an example of why black market doesn't work, and rebuttal units, which I will discuss in detail in the next part of the tutorial. So for nearly all corpus, we've written at least one, usually much more text for each type. So I think you can appreciate this was a big effort. For the remaining of this part of the tutorial, let me talk about related work. So one thing which is reminiscent of our work is argumentation schemes. There's a series of works about it, which is led by Doug Walton. And you can see the book from 2008, but there is also a subsequent work. So for example, the following argument is considered an argument from expert opinion. Dr. Zhivago said that regions which adopted telemedicine have seen a sharp decline in public health. This is an argument from expert opinion for the motion of telemedicine. So argumentation schemes are a categorization of arguments which is kind of similar to what we have in the sense that the arguments that we've written are categorized according to the classes. They are based on patterns of reasoning rather than the semantic aspects. They also instruct how to critically examine an argument, which is not something that we have. But on the other hand, it does not suggest how to make a concrete argument. And you don't even know if specific argumentation schemes are relevant to specific motions or not. So there are similarities, but I think it's quite a different thing. Another thing which is related and we touched upon before is framing. We said that one of the advantages of having these classes of principled arguments is trying to frame the debate in a way which is favorable to us. So there is a lot of work on framing in the social science, which unfortunately I'm not familiar with, and so I've listed some examples here below. A couple of things which I've seen that's been done there is that there is a categorization of how information is framed, so the types of frames that exist, like fairness and equality or crime and punishment. And in this sense, it's similar to the kind of things that we try to do in modeling principled arguments. And also, there are works which make a distinction between specific frames and general frames. And I think our work on recurring arguments is very similar to general frames. Framing has also been studied in the NLP community. So let me touch upon two datasets which are relevant. One is the media frames corpus from Card and others. It's a dataset of 15,000 articles on 3 topics. Texts are annotated for 15 frames, like legality and politics and economics. Nearly all frames appear in all topics, so it's a very dense matrix. But the main thing that subsequent work focused on is the primary frame of the article, the main thing that the article talks about. And most of the works talk about the immigration article. And one of the interesting work done on this is by Naderi and Hurst from 2017. And they did sentence level classification for these immigration articles and tried to determine the frame, and they have achieved an accuracy of nearly 60%. So it kind of has the same flavor as what we did. But it comes from a very different perspective. And also in terms of size, there are 3 topics which are studied, and most of work actually focuses on this one topic of immigration, which is very different from our work where we have nearly 700 topics. But it does raise an interesting research question for further research, is can we, like similarly to the work of Naderi and Hurst, when we're given a sentence or an argument, try to predict not its frame, but its class, if one exists. Another dataset related to framing is from Azure et al. And this dataset is based on 12,000 arguments coming from Debatopedia for 465 topics. And Debatopedia, they have the aspect of an argument or of a set of arguments, and Azure et al. Consider this aspect the frame. As in the work on social science, in the social science that I've mentioned, they see that most frames are specific, they belong to one topic, but some 4% of them are general, they belong to more than 4 topics. And what they do is they try in an unsupervised manner to try and reconstruct argument clusters. And the related work, which doesn't actually build on that, but sort of maybe borrows ideas from there, is how to generate arguments. And specifically, if you're given a stance, a topic, and an aspect or a frame, can you generate an argument for the topic with this stance which discusses this aspect? Which raises an interesting research question in our context, is can we generate arguments for a specific COPA? That is, we're given a topic, a stance, and a COPA. Can we generate the argument from this COPA for this topic and stance? And finally, there is a work which also I'm not really familiar about, ideology. And one of the works suggests a 12-item scale to measure conservatism. And so some of the items on this scale are abortion, welfare, tax, immigration, big government, and so on. And what's interesting is that many of these items coincide with our classes of general arguments. So abortion is very specific. I would say that it only pertains to the motion about, or to motions about abortion. But things like welfare, big government, national security, and religion are commonplace in our motion sets and in general. If you're interested in more details, most of what I've spoken about appears in our ACL 2019 paper. And, let me thank all of you for listening, for all the people who helped in developing this project, and specifically and most of all to Riel Gera, Daniel Hershkovitz, and Asaf Gavron, who have been my collaborators on this work for several years. Thank you. Hello, and welcome to the fifth part of the Advances in Debating Technologies tutorial, which is about listening comprehension and rebuttal. The work I'll describe is mostly based on these 6 papers, coming from Shachar Mirkin and others, Tamar Levy and others, and Natan Orbach and others, over the course of some 3 years. So to define broadly the speech rebuttal task, we can think of it as follows. There is speech audio, which needs to be translated into speech text using automatic speech recognition. Then, using natural language understanding, we need to identify the arguments which have been made in the speech. We need to come up with counter-arguments, and they have an argument rebuttal. Then, using natural language generation to generate the actual arguments within the context of a rebuttal speech. And finally, using expressive text-to-speech to generate the audio spoken by the debater system. If you're at all familiar with dialogue systems, the classic architecture of dialogue systems, especially of task-oriented ones, is very similar, where the very right part is slightly different, but also analogous. So dialogue systems are usually split into 2 types: the task-oriented dialogue systems, such as a system that orders a table for you at restaurants or informs you of a bus route. Usually these systems are based on slot filling, so if you want to order a table at the restaurant, the system will need to fill in the slot for day, time, the name of the restaurant, and so on. And these systems are usually rule-based, or usually has been rule-based, with some recent works replacing some of the components with neural components. But as far as I know, these kind of systems are usually not trained end-to-end. By contrast, the other type of dialogue systems, the chit-chat systems, the modern ones are end-to-end. The goal there is mainly to keep the user engaged. And as I said, modern systems are end-to-end. They're usually transformer-based. Essentially, it's a language model that tries to predict the correct response in the same way you would predict the next word or the next sentence. And there are also hybrid systems which sort of combine the two. For example, you could have a task-oriented system, but when the user goes off script or something like that, it might employ a chit-chat backup. So let's compare rebuttal to these 2 types of dialogue system. So the topic of what we're discussing, or what we're talking about, for task-oriented is well-defined, such as a system that orders a table at a restaurant. For chit-chat, it's completely open. And for a rebuttal system, at least in our context, it's fairly open, but we know that we're going to discuss some controversial topics. So this narrows the scope a little bit. The goal in task-oriented system is very well defined. Order a table. For chit-chat, it's quite open as well. You could say that the goal is to keep the user engaged. And in the rebuttal, it's kind of tricky. The goal is to persuade an audience, so to persuade a third party that our stance is correct rather than the other side. And the length of the utterances in both types of dialogue systems is typically short. Also, in task-oriented systems, the entire conversation is usually kind of short, whereas a rebuttal in the context of a debate, the utterances of the other side are long. So the speech is 4 minutes rather than a couple of sentences. On the other hand, The number of rounds is short. It's only 3 rounds. And the role of the user is distinctly different in rebuttal systems and in dialogue systems. In dialogue systems, the user is usually cooperative, or at least curious, cooperative in the sense that if the system misses something, the user has motivation to correct it, to explain that the date or the name of the restaurant was misinterpreted. Whereas when in the context of a debate, the user is opposing the system, and if the system makes a mistake, the user is likely to take advantage of it rather than correct it. In terms of the natural language understanding task, the main thing in task-oriented system is to recognize the slot fillers and to fill in the correct slot so it can make the correct reservation. For chit-chat systems, it's also quite open, mainly to remain coherent. And in the rebuttal task, it's arguably a more deeper and a more complex natural understanding task. We're trying to understand what were the main points, or at least some of them, that were made by the speaker. As far as data goes, for training the system, for task-oriented systems, when it's a new system, a new task, usually data is limited, but it could depend on the task. For chit-chat, you potentially have lots of data, and for rebuttal, the data is very limited, especially if you're thinking of a specific context. And I've hinted at this in the previous slide. Let's think about the price of error. So here is a sample conversation from the Mina paper. Mina asks the human, have you seen 12 Angry Men or in Bruges? The human says no and no. Mina says it highly recommends them. There's a little bit of a chat after that. And then the human asks, okay, who are the main characters? Mina says Kristen Stewart and Ben Affleck do not appear in either of these two movies. Human is confused, asks in which movie. Mina said The Runaways. The user tries to understand what's going on, so not in any of the two you mentioned earlier. And the system confirms, yes, it's not. No, it's not in any of the movies I mentioned earlier. So the system arguably made a mistake, but the user is cooperative and helps the system correct the mistake and clarify what's going on. Whereas in a debate, the two sides are contesting, and the human will not be cooperative. So also the fact that the utterances are short allows the system to recover quickly. It can recover right after the human reflects the error. And if the mistakes are amusing, like in this case, maybe they're not that bad. Maybe the user is actually amused and wants to continue the conversation. Okay, so the speech rebuttal task, as we described, can be roughly illustrated as follows. And in the following slides, I will talk about the right-hand side, about how do we understand which arguments we need to address and how do we counter them. So the key architectural unit is what we call the rebuttal unit. It's composed of 3 parts. The query, which defines what the opponent might claim. This is what we will look for in the opponent's speech. The quoted claim, which is how are we going to refer to this claim or argument. This claim might be implicit, so we can't really quote from what the user actually said. And finally, the rebuttal argument, how we're going to respond. The important thing here is that the rebuttal unit is defined in advance, and through the query tries to predict what the user might say and then to confirm it after the user actually gave his or her speech. So for example, suppose the debate topic is telemedicine, and the rebuttal unit might look like this. The query would be degraded care. We presume beforehand that the user, the opponent, might say something about degraded care in telemedicine. And if we match that to the user's speech, we can quote the user as saying the care offered by telemedicine is not as good as traditional one, and rebut this claim by saying that comparative evidence have found no correlation between telemedicine and patient's prognosis. Okay, so to make this more explicit, the algorithm would be to check if the opponent mentioned any of the queries. Suppose we have several rebuttal units, we will check each query and each rebuttal unit. Then decide which rebuttal units were actually made and which of them should be used in the rebuttal speech. We'll use the quoted claim to refer to what the opponent said, and the rebuttal argument to make the actual rebuttal in the speech. The challenge is therefore to construct rebuttal units when the topic is not known in advance. And more importantly, when we don't know what the user would say in advance. But the advantage, at least when you're thinking of a debating system such as ours, coming from IBM, where we really care about making embarrassing mistakes, and that all potential responses are known in advance. So we can go over all potential, at least in theory, we can go over all potential responses in advance before the speech is made, and make sure that nothing truly embarrassing might be said. Okay. There are multiple types of rebuttal used in the debater system. I will describe two of them. One is the copper-based one, text which is based on recurring debate themes. So this is based on the ideas I've discussed in the previous part of the tutorial. If you have not seen it, maybe check it out before continuing with this one. So for example, a recurring theme, class of principled argument is the black market. So we can have a query asking whether or not the opponent claimed something about a black market. And then when we refer to what the opponent said, we would say that the opponent said that the black market will rise. And as rebuttal, we could say that even if there is some truth to that, it should not stop us from doing what is right. So this is a rebuttal unit, the query, the quoted text, the rebuttal. Based on this, we can embed within the rebuttal speech a rebuttal of the opponent. So if a COPA is matched to a debate topic, all its rebuttal units are candidates. Each COPA has a list of rebuttal units of scripted or pre-authored units which are relevant to this class. And if the class is matched to the motion, then all such units are potential candidates. All these queries will be checked whether or not they were mentioned in the opponent's speech. Another type of rebuttal unit is one which is based on argument mining. So when we do argument mining, we're mainly interested in finding claims for the debater system to present, but we can also look for claims of opposing stance, and then these can be queries for the rebuttal units. These are claims which the opponent might say. When we quote, we just use the same claim we used for a query. And as a rebuttal, we can use evidence of opposing stance, of our stance, which are related to the claim. For example, which makes mention of the same topics. For example, the query and quoted claim when we're discussing telemedicine might be telemedicine is unpleasant for both patients and doctors. This is a claim found through argument mining with an opposing stance. If the user, the opponent, made this claim, we could rebut it with an evidence which also talks about the same kind of thing. For example, a doctor saying that telemedicine has been a positive experience for patients, their families, and staff. So what are the challenges presented by the method I've just described? First, how do we determine whether a query was mentioned by the opponent? Suppose we can think of an algorithm that does that. How do we evaluate it? How do we evaluate the rebuttal system? And if we want to evaluate the rebuttal system, we probably need some labeled data. So how do we collect this data and how do we label it? So let's start with the end. Let's start with data collection. So we employed a team of 10 academic debaters from both the US and Israel. We defined a set of motions for which the data would be collected or defined. For each motion, within this set of motion, we recorded several opening speeches. More precisely, these academic debaters recorded these opening speeches. And then each debater received one of the recorded speeches from a different debater and recorded a response speech, a rebuttal speech. In total, we collected some 3,500 speeches this way, which are available to download as part of our paper by Orbach and others from 2020. Okay, so now let's discuss the annotation task, which is the following. Given a speech and a set of claim queries, mark which claims are mentioned in the speech, which queries should be defined as matching. So you can do this in a straightforward manner when you have an expert workforce and when you have a small set of claims, which is how we started it, which we've indeed done. But when we tried to scale, when we tried to use crowd workers and process a large number of claims and speeches, this was challenging. You could think that you can just label pairs of queries and speech sentences for all potential queries and for all sentences in the speech. But there are too many pairs for exhaustive annotation, even with crowd work. Only a small fraction would be positive. Usually queries don't match a specific sentence. So even if you sample most of the pairs that you will sample, nearly all of them would be negative example. And finally, to say whether or not a query matches, for example, whether or not a speech talks about the danger of a rising black market, sometimes you can't do it from a single sentence. The context does matter. Sometimes there isn't a specific sentence in which the claim was made, but overall, when you read the entire speech, you would say that the claim was implicitly made. So how do we address this problem, this same task, which is challenging at a scale? First, we cultivated a suitable crowd workforce. So if you just use crowd workers, we got very poor results. But if you try this and pick the good workers, the good annotators, you can cultivate one which is analogous to the expert workforce that we had working in-house. So to do this, you post the tasks both in a general channel where you expect much of the work to be poor, but from which you can identify the good workers, and also in the dedicated channel, where you trust the annotations much more. We've done this in Crowdflower, which was later Figure 8 and is now called Appen. As I said, you identify the good annotators and add them to the dedicated channel. To identify the good annotators, you can look at things like shared IPs. It's one of the things we've noticed, that when you have two people from the same IP, two users from the same IP, the annotation tends to be suspiciously similar. So you can also look directly at the correlation between the annotators. If they annotate the same, then maybe it's the same person or two persons sitting by each other and doing the work together, or by the fraction of positives if it's very different from what you'd expect, and so on. So in a paper by Tamar Levy and others, this is explained in detail. And also, you can use test questions in post-processing. So what Appen allows you to do is have test questions within the task, and based on that, filter out the annotators. But there are tricks the annotators learn how to overcome this. And what you could do is filter the annotators in post-processing. So this comes at a cost that you have to throw away some of the annotations which you paid for, but it allows you much better to identify the good ones and to give them bonuses. So you promise bonuses beforehand, and based on the post-annotation evaluation, you give the bonuses, and in this way you cultivate a workforce which is motivated to take the work seriously, and which learns to trust that they will indeed get the bonuses that you promised. The labels that we defined when the claims were mentioned, were annotated versus a speech, were whether the claim was mentioned explicitly, implicitly, or not mentioned at all. For example, this is an example with mind claims. The candidates come from a mind claim. Suppose there is this part of the speech talking about whether or not we should support water fluoridation. And so consider the claim water fluoridation has no side effects. The claim water fluoridation is safe and effective. And the claim most people wouldn't get regular fluoride treatment at the dentist. All of these are claims which support the fluoridation of water. The first one is explicit. The speech actually says there are no proofing side effects. The second one is implicit. You can't really pinpoint where it's said, but the overall message from this paragraph is that water fluoridation is safe and effective. And the third one is not mentioned at all. Okay, so we've discussed how to annotate whether a query matches a speech. Now let's ask ourselves how to do this algorithmically. Let's start with the COPPA-based rebuttal units. So for such queries, we can compute an a priori probability that the query will be matched. Because these queries are based on recurring themes, the same query can come from a class that matches several motions. So we can ask in how many speeches the query was labeled as positive in comparison to the number of speeches in which the query was a candidate, in which the COPPA from which the query comes was matched to the motion. This gives us an a priori probability that the query will be a positive match to the speech, and this gives us a trivial, but as you'll see, powerful baseline for picking a rebuttal unit. We can simply pick the rebuttal unit with the highest a priori probability. In the more general case, when we can't compute an a priori probability or we don't want to, we can use other matching methods, which are sentence by sentence based. For example, keyword matching. So the query might be a keyword like black market, as we've seen before. And then we go over the speech sentence by sentence and look whether or not the keyword matches. Similarly, we've developed a Siamese network that tries to determine whether or not a sentence matches a query. We've used a word-to-vec based sentence matching, and we used more recently BERT-based sentence matching. As you can see, the BERT-based method performs fairly well. These are the blue lines, and there's some difference between how the two BERT models were trained. This is the solid line and the dot line. But what you can also see that the trivial, the a priori probability baseline is a very challenging baseline to beat. So of course it has many disadvantages, not only from a scientific point of view, but also from a practical point of view. It will always suggest the same lead for the same class, the one with the highest a priori probability. But I think maybe you can look at this graph and be happy that there is room for more work on this and to improve, that you have this powerful trivial baseline to try and beat, and that modern methods such as fine-tuned BERT already do something, already are able to make some of the way toward this difficult trivial baseline. So to recap, how does the system work? We start with a motion. We do COPPA matching to the motion. Then we have a set of classes which match this motion. We also do argument mining, and we find arguments, namely claims, which oppose our stance towards the motion, which have the opposite stance. Based on these, we build the rebuttal units. We're mostly interested in the fact that a rebuttal unit has a query, which we can look for in the speech, and a rebuttal, which says how to answer it. All this can be done before our opponent spoke. Then we get the opponent's speech by having the debater speak and using automatic speech recognition. Then we do query matching. We match the queries to the text that came out of the automatic speech recognition. This may give us several matching rebuttal units. These matched rebuttal units are ranked and passed on to the speech construction to be embedded within the speech. And to clarify, how do we build the rebuttal units? Or you can think of it as the following claim or related task. Given a claim, output an argument countering this claim. So in our case, in the COPPA-based rebuttal, the rebuttal unit is authored as a whole. So there is no challenge. In the case of the argument mining-based rebuttal units, where the query is a claim and rebuttal argument is an evidence of an opposing stance, we use the simple heuristic. And another related question is, given a set of potential rebuttals, which ones to choose? And also here we've used the simple heuristic of how to rank them. And if we're thinking of future work, then another thing we could ask ourselves is, can we generate a rebuttal de novo? Can we see the opponent's speech and generate the argument rather than writing it or detecting it in advance? So this brings me to the related work. So one work I want to mention is work by Henning Wachsmuth and others called Retrieval of the Best Counter-Argument with Prior Topic Knowledge. In this work, they looked at arguments coming from iDebate. So this is a database with motions, such as this house would have a second Brexit referendum before leaving the EU. And for each motion, they have several points. And for each point, they have a counterpoint. So the task that Henning and his colleagues considered is, suppose I show you a point, and I show you several counterpoints. Can you determine automatically which of the counterpoint is the correct counterpoint for this point? So this is a step towards building a rebuttal. It assumes that you have, like in our case, a claim and the counterclaim, but you have several counterclaims, and you want to pick the correct one or the best one. And they they suggest an algorithm for how to do this. They try to maximize the topic similarity between the point and the counterpoint, while at the same time maximizing the stance dissimilarity. And both of these measures are based on the distance between embedding vectors and between term frequencies. So you can look at their very nice paper for the details. And I've mentioned the end of the slide culminating our work, and that it might be interesting to generate rebuttal arguments de novo. So there are a couple of works exploring this possibility from Xinyu Hua and Lu Wang and Zelu. What they do is they train a BiLSTM encoder decoder in a two-step manner. First, they decode talking points. So this is similar like to aspects maybe. And then they attend them and the actual claim to decode a counter-argument. They train on data coming from the Change My View subreddit, which is very popular in the field. And they have additional input. They retrieve Wikipedia articles which are related to the claim for which they're trying to construct a counter-argument. And they extract sentences that are likely to be relevant as evidence, and from them they generate the counter-argument, so you could say it's not completely de novo. A different approach towards neural generation is from Schiller et al., which I've mentioned briefly in the previous part of the tutorial. So their work is based on the CTRL language model. This language model takes a control sequence as input and outputs coherent text. So if you're familiar with, say, GPT-2, it's kind of similar, but instead of getting a sentence as input, in this case, they take a control sequence. Schiller et al. Define the control sequence as a topic, stance, and aspect. And then when they have several arguments which are being generated, they rank them or filter them using an argument quality evaluator from Gretz et al. From our group. So you can think of this as a way of doing a rebuttal, not a rebuttal of a claim, but a rebuttal of a topic, or having counter-argument for arguments supporting the topic. And here is an example. When the topic is nuclear energy, the stance can be pro or con in the second case. The aspect is safe in the first case and leak in the second case. And you can see that the first argument is fairly well written. The second one is less coherent. And accordingly, the argument quality score in the first case is high, and in the second case, it's mediocre. And the training data they used for fine-tuning is based on argument mining that they done on the Common Crawl and on Reddit. This gives them annotated arguments, argument mining, gives them arguments, and also gives them the stance. Then they need to decide what the aspect is. So they fine-tune Burton arguments, which are manually annotated for the aspect, and obtain a classifier that tells them what the aspect is. And then they use this to further annotate their dataset for aspect. And there are a couple of similar works which appeared at the same time as this one from Schialom and others, and one from Shaigret and others. I mentioned Shai in the previous slide. This is work on argument quality. A different way to look at the rebuttal question is to ask, what do you want to rebut? So in this work by Jo and others, they've looked at the subreddit Change My View. Suppose you have this post on Change My View, someone saying, I believe that communism is not as bad as everyone says, change my view. They ask which of the sentences in this paragraph in which the original poster describes their current view one should attack in order to change that person's view. So in the reply, sometimes, perhaps often, the replier quotes a specific sentence and then suggests a counter-argument. So here is the sentence, the first sentence, which the user is trying to rebut, and this is the second one. And then sometimes a discussion follows, and eventually the original poster may change their view, and then they have this small delta sign when they begin their final post. And this means that they indeed change their view, and Jo et al. Take this as an indication that the sentences which were rebutted are sentences which should be indeed attacked. They are the attackable sentences in the arguments. So they label sentences either successfully attacked, unsuccessfully attacked, or not attacked. And they fine-tune BERT to identify either attacked sentences, so this would be successfully and unsuccessfully attacked, or just to identify successfully attacked sentences. And they get results which I think are very interesting and really open the way for further research. You can see that the BERT model that they fine-tune is about as successful as the human annotators they've used. But you can also see that these numbers are not very high. And I think this is a very interesting question, but maybe there is more work needs to be done on how actually to define it in a way which is clearer so that humans can agree on it better. So this brings me to the end of this part of the tutorial. I would like to thank all the people who worked on the Rebuttal project and the debater over the years, Shachar Mirkin, Matan Orbach, and Tamar Levy, which I've mentioned, and also Lily Kolterman, Lena Duncan, and Yoav Kantor. And also thank you for listening.
Hello and welcome to the 6th part of Advances in Debating Technologies tutorial, which will focus on basic NLP capabilities. One of the basic capabilities which was developed in Project Debater is wikification. Wikification is a way to enrich texts by linking words and phrases to their corresponding Wikipedia articles. In this example, the wikification process resulted in linking the phrase physical discipline to the Wikipedia page corporal punishment, psychological was linked to psychology, and aggressive to aggression. The main motivation for developing a wikification tool comes from argument mining. All queries of the argument mining component contain the topic as one of their elements. However, a topic can be expressed in multiple ways, as can be seen in the following example. Physical punishment and physical discipline are different ways to express the concept corporal punishment. Wikification maps all these different lexical forms onto the same Wikipedia concept. Thanks to the Wikification tool, the system retrieved this relevant argument among the query results. Without Wikification, the amount and coverage of the extracted arguments would probably be much smaller. But in order to use Wikification in the query-based retrieval process, it is necessary to wikify the entire corpus, 10 billion sentences. This is not feasible for most existing Wikification tools, which rely on expensive context-based algorithms for performing the mapping process. This paper by Ilya Schneiderman et al. Presents the runtime-oriented Wikification tool, which was developed in Project Debater in order to enable the Wikification of the entire corpus. The tool leverages the redirect mechanism of Wikipedia for performing the mapping between terms and Wikipedia pages. The terms are mapped to the same page they are sent to by the redirect mechanism. This lightweight Wikification tool is able to wikify the entire corpus in 40 hours compared to the 22 days it took to its counterpart, Tagme. Another important task which required developing new NLP capabilities in Project Debater is the organization of the argumentative units into thematic paragraphs. Here we see a list of arguments that support the motion trans fats usage in food should be banned. In order to create a coherent and well-organized speech, we would like to group together arguments that refer to the same aspect of the topic. Here we see how the sentences can be grouped together based on their thematic similarity. The two green sentences are thematically related since they both refer to the mental health aspect of trans fats. Similarly, the purple sentences discuss the fertility aspect, while the blue ones deal with the influence of trans fats on children's health. In Project Debater, the organization of argumentative texts is performed by clustering them using the iClust algorithm. But clustering requires a similarity function between sentences. If we look, for example, at the arguments that refer to the infertility aspect, we see that they contain related Wikipedia concepts such as sperm and infertility. In general, arguments of the same theme tend to share Wikipedia concepts that are related to this theme. So a possible way to measure thematic similarity between sentences is to measure the relatedness between their Wikipedia concepts. But how the relatedness between pairs of concepts can be measured? We coped with this problem by first creating a benchmark of concept pairs annotated for their level of relatedness. We then used this benchmark to train a supervised model for predicting the level of relatedness between unseen pairs. The resultant concept relatedness benchmark is the first human annotated dataset of Wikipedia concepts with more than 19,000 pairs of concepts. We use this benchmark to develop a tool for measuring level of relatedness between concepts. At earlier stages of the project, we created a term relatedness benchmark, which has been used to learn a model for measuring similarities between terms. Besides being the largest term relatedness benchmark, one of its main advantages compared to its counterparts is that it includes not only unigrams but also multi-word terms which are ubiquitous in natural language. A different approach for measuring similarity between sentences is representation learning. In this approach, a DNN is used to embed sentences in a vector space. We adopted this approach for learning sentence embeddings that are tailored for capturing thematic similarity. We created a weakly labeled dataset of thematic similarity by leveraging the partition of Wikipedia articles into sections. The underlying assumption was simple. Sentences from the same section are more thematically related than sentences from different sections. Based on this heuristic, we created 1.8 million sentence triplets composed of a pivot sentence, another sentence from the same section, and another sentence from a different section. We used the triplet network to learn the sentence embeddings and used the triplet loss function to encourage the network to embed sentences from the same section closely. To summarize, we created a lightweight end-to-end wikification tool based on redirects that enabled us to wikify the entire corpus. For the problem of creating thematic clusters, we created a large term relatedness dataset with 10,000 pairs that goes beyond unigrams. And we also created a large concept-related dataset with more than 19,000 pairs. In addition, we developed a tool for measuring relatedness between concepts based on supervised learning from the concept-relatedness dataset. We developed a deep learning solution for learning thematic similarity between sentences. And finally, we created a thematic clustering dataset based on Wikipedia sections. In a recent work, Reimers and Gurevich introduced sentence BERT. They used Siamese triplet variants of BERT to compute semantically meaningful sentence embeddings. Sentence BERT was fine-tuned on our weakly labeled triplet dataset that we described earlier. The results of the paper show that sentence BERT outperforms other networks on the triplet classification task. Sentence BERT has not been applied to the task of thematic clustering, but the success it shows on the triplet classification task is a good indication for its potential effectiveness in the task of thematic clustering as well. Finally, I would like to refer you to 3 recent papers that suggest alternative approaches for dealing with the challenging task of thematic clustering. I believe that reviewing these papers in conjunction with our thematic clustering papers should provide a good overview of the problem and the possible alternatives for attacking it. Thank you very much for your time.
Welcome to the 7th part of the Debating Technologies tutorial, From Arguments to Narrative. By now, we have all the ingredients for creating a speech. Rank lists of automatically extracted claims and evidence that support our stance, rebuttal units, argumentative texts manually composed for classes of principled arguments or corpus, boilerplate texts, debate topic definition from Wikipedia, and more. In this part of the tutorial, I will give you the recipe for generating speeches from these ingredients. Here you can see the various stages in the debate construction flow. Let's discuss each of these stages. The first stage is argument filtering. We filter arguments for several reasons. The confidence assigned by the claim detection or evidence detection classifier is not high enough. The stance confidence is not high enough. They are too long or too short, or their content or style are inappropriate. Next, we want to remove nearly identical arguments to avoid repetitions in the speech. We perform agglomerative clustering using weighted word-to-vec similarity and keep one representative per cluster. An important subtask in debate construction is to organize the extracted arguments into coherent paragraphs. To this end, we performed thematic clustering of the arguments. Each paragraph will be created from one of these clusters. A thematic clustering method was described by Liat in the previous section. The next step in the pipeline is a theme extraction. For each cluster, we extract a theme which is a Wikipedia concept. We select a theme that is both statistically enriched and frequent in the cluster. In addition, we aim to extract a theme claim. This is a simple claim that captures the relation between the theme and the debate topic. When constructing the speech, we will use this theme claim to introduce the theme, and we will see an example later. We will now take a deeper look at the last two stages in the pipeline, rephrasing and speech generation. The arguments we use in the speech were extracted from many different documents. Combining them into a coherent and fluent paragraph is a really challenging task. There are many issues that need to be addressed. To achieve this goal, the system employs as many as 62 different rephrasers. Some of these rephrasers operate at the argument level, others consider the whole paragraph. Some of the basic rephrasers perform anaphora resolution or do the inverse of anaphora resolution, namely, replace a repeating noun phrase with an anaphor. They can also combine several short arguments into a single sentence. Let's look at a more advanced example of rephrasing. Consider the following evidence. Brian Kaplan argues that higher education is a big waste of time and money, and that students spend thousands of hours studying subjects irrelevant to the modern labor market. Are you impressed with this evidence? Perhaps not so much, because we don't know who Brian Kaplan is. Okay, so now we are more impressed knowing that he is an economics professor at George Mason University. So this rephraser looks for this description in the same document where the argument was found and adds it in the right place. Let's have a look at another rephrasing example. This example highlights another issue, the difference between written language, such as news articles from which the arguments were extracted, and spoken language, which is what we are trying to generate. The phrasing in the example, where the part indicating who the quote is from, appearing at the end, is fine for written language, but for spoken language, it is confusing. The rephraser fixes this problem by moving this part to the beginning of the argument. Finally, speech is generated based on templates that define its structure. Here's an example for the motion, "We should not abandon the Paris Agreement." The speech begins with a greeting. Then, if the debate topic is not a common phrase, it will provide a definition for it. In our case, definition of the Paris Agreement. The debate topic is matched to the environment class, so we continue with opening text composed for this class, followed by principal arguments against harming the environment. Next, we have text introducing the themes which the speech is going to discuss. You can see in bold a theme claim introducing the theme of climate change. The Paris Climate Accord represents the best way to address climate change. Next, we have 3 paragraphs constructed from the thematic clusters, then argument summary and pre-closing. Then in some cases, we may have a proactive argument aiming to predict the opponent's argument and provide rebuttal in advance. For example, my co-debater today will likely say that immediate human interests come first, I would like them to supply evidence showing how ruining the environment would benefit anyone in the long run. And finally, we have the closing of the speech. In the second and third speeches, we will also include rebuttal paragraph. Here's an example. I will just give you a few seconds to read it. One of the challenges in delivering a 4-minute speech is to keep it lively and to keep the audience engaged. One way to achieve this is by using humor, as shown in the following example taken from one of the training debates we had while developing the system.
IBM Debater can have all the opinions in the world, but IBM Debater does not pay taxes, and we do.
You are speaking at the extremely fast rate of 218 words per minute. There is no need to hurry.
So, as you can see, both Chaya the human debater and Project Debater used humor. Chaya made a joke about Project Debater not paying taxes, and Project Debater commented about Chaya speaking too fast. Here is another example of humorous text, which was written for the theme poverty. While I cannot experience poverty directly and have no complaints concerning my own standards of living, I still have the following to share. This text was automatically selected for the debate with Harish Natarajan about subsidizing preschools. Such texts are a way to give Project Debater AI personality in a humorous and fun way. We now reached the final words of the debate, and we end it with a pre-composed text for the environment class, which, as I mentioned, was automatically matched to the Paris Agreement motion. And it's always good to finish with a strong quote, in this case by Mahatma Gandhi. And with that, we will also end this session. Thank you for watching.
Hello and welcome to the last part of the tutorial on advances in debating technologies, where we will aim to summarize what we discussed so far and talk a little bit about moving forward. So first, let us take a step back from all the details and think about the challenges that one should probably address when trying to develop a live debate system. Let's start by considering the opening speech, which is around 4 minutes long in our case, containing between 600 to 700 words. This is reminiscent to an opinion article that you may encounter in your favorite newspaper, but in the case of Project Debater, it is written in a completely automatic manner on a topic that was never included in the training data of the system. And in parts 2, 3, 6, and 7, we discussed some of the underlying capabilities that were needed to address this challenge. Next, listening comprehension or rebuttal. We may compare that to the virtual assistants that we are familiar with and often have on our phones, but these assistants usually need to respond to a single sentence with a functional flavor, like turn off the lights or find me a restaurant nearby. And in contrast, in a live debate, we are in a different situation. The system needs to listen to the opponent, and the opponent is speaking fast with a lot of emotion, raising various arguments and ethical considerations, and still the system needs somehow to understand the gist of that in order to properly respond. And again, this is quite a challenging task, and in part 5 we discussed how we address that in Project Debater, but I think it is fair to say that we are still far from having general good solutions to this problem. And finally, modeling human dilemma is needed in order to formally capture and then leverage the commonalities between different debates that humans are having, and we heard about that in part 4 of this tutorial. And the problem, of course, is that to participate in a live debate in such a way, many underlying capabilities need to work well simultaneously. And in practice, of course, many things may go wrong, sometimes in unexpected ways. So for example, if you get the stance wrong, you may end up arguing in favor of your opponent, which is not a recommended tactic based on our own experience. In addition, the system may drift from the topic. Many of our team members still vividly remember one of the first live debates that we had with the system back in 2016, where the debate was about whether or not physical education should be compulsory, and the debater system gradually started to argue in passion about the benefits of sex education, and the human debater was desperately trying to bring it back on track in vain, which was quite an amusing experience for some people in the audience and perhaps disturbing for some other people, depending on your perspective, I guess. In addition, the system is only as good as its corpus. So, for example, it may quote a sentence about a malaria virus, even though it is a parasite, not a virus, and so on. In addition, as we know from other fields as well, sarcasm is hard to detect. So the system may quote a sentence with a claim by scientists, missing the quote-unquote part, and therefore missing the real meaning of this sentence. And things can get even more complicated. So for example, as mentioned in part 4, when using a principal argument, often we use simple slot filling techniques in order to adjust the argument a little bit to make it sound even more relevant to this specific debate. So for example, in a debate about whether or not we should ban gambling, instead of saying people enjoy that, therefore, we say people enjoy gambling, therefore we should attempt to fix it rather than eliminate it. And in this case, but in another debate, you may end up saying people enjoy assisted suicide, therefore we should attempt to fix it rather than eliminate it, which may sound a bit disturbing, at least to some people. And similarly, as mentioned in part 2, sometimes we try to expand the scope of the debate by automatically identifying the alternative to the topic that is explicitly stated in the motion. So, for example, in a debate about the pros and cons of surrogacy, we may end up saying, let me discuss a welcome alternative to surrogacy. This is adoption, which sounds fine. But in a different debate, we may end up saying, let me discuss a welcome alternative to global warming. This is global cooling, which again is probably not ideal. And it can get even worse, since in a different debate, we may even say, let me discuss an alternative to suicide, which has some advantages. This is homicide. And as you can imagine, probably this will not be perceived well by some people in the audience. And still, despite these challenges, we were able to make progress. And the first full live debates that we had with the system were early in 2016, after nearly 4 years of work. And during these early experiments, the system was really at a toddler level and was not making a lot of sense. But in only 3 years, we were able to advance from toddler level up to good university level debater, which was an interesting experience and nice to observe. And from a more quantitative perspective, we needed to evaluate the performance of the system over the years, and this evaluation is a significant challenge by itself. And to address that, we considered a set of around 80 motions, and for each motion, we sent 3 speeches for annotation by a team of in-house human annotators. The opening speech of the system, then an opening speech by a human debater representing the opposition, and finally a corresponding rebuttal speech by project debater. And on the left panel, we see the results of this periodic evaluation for nearly 3 years, averaged over these 80 motions or so. So and on the right, we see the results for the top quartile of the motions. And while there is clearly high variance in the performance of the system over different motions, we still see a nice and steady, significant improvement from year to year, reflecting the gradual improvement in the performance of the system in its entirety. Next, let us discuss a little bit what happened since the demonstration of the live debate system last year. So first of all, the work on Project Debater should be perceived as part of a wider journey taken by IBM Research to develop technologies that eventually will be able to master human language. The mission of the debater team in this context is to develop language technologies that will be able to enhance decision-making in enterprises. And when we need to take a decision, this means that we face a complex question, one that do not have a simple factual answer. Rather, what you have are pros and cons that need be carefully considered. And when thinking about that, at some point we started to think about new use cases, debater speech by crowd and debater key point analysis, which I will discuss. And specifically, we thought about the following question: what will happen if we will pose a controversial topic to many different individuals, thousands of people, and ask them to share their opinions in the form of a pro or a con argument? Can we use debating technologies in order to generate a valuable and compelling narrative out of all these individual contributions? And what are the challenges involved in doing so? So first, we need to automatically identify the stance of each argument, so we will place it in the correct narrative. We also need to expect that different people will make the same argument only using different words, so we need somehow to automatically identify these paraphrases and remove this redundancy. In addition, we need to automatically identify the underlying themes that will spontaneously emerge from all these individual contributions. And finally, there is this vague but highly important issue of argument quality already discussed in part 3 of this tutorial. So often when we show people two arguments, they would agree that one is more persuasive than the other, but what are the underlying mechanisms that guide us to prefer one argument over the other? And how do you train an AI system to identify the top quality arguments so we can draw the attention of the decision maker to these arguments first? We heard more about that in part 3 of this tutorial. And after addressing these issues and other challenges, we showed that we can indeed generate a coherent and compelling narrative out of the arguments contributed by many different people, thousands of individuals. And we demonstrated this system, which we refer to as debater speech by crowd, in several events, including a very interesting debate that we had last year in Cambridge, UK, which you can see, and you can see a picture from this debate in the slide, where the debater system used speech by crowd in order to represent the voice of the people delivering the pro and con opening speeches of the debate, and then the debate proceeded by human experts. The topic of that debate, by the way, was whether artificial intelligence will bring more harm than good. But of course, beyond demonstrations, this kind of application can be useful in the real world. And for example, think of a company that would like to collect the opinions of thousands of customers about a product or a service being offered, or an employer that would like to hear the voice of the employees about various topics, or even a government that would like to gain the opinions of the citizens about a policy being examined. So, for example, social distancing, lockdowns, etc., if we would like to think about some contemporary examples. So in a sense, we think that this technology can be used in order to form an effective communication channel between the decision makers and the people that might be impacted by the decision, and it could be quite valuable in this manner. Taking this idea one step further, we realized at some point that while generating a narrative is nice, there are additional aspects that could be quite important. And in a narrative, we often wish to avoid redundancy. However, the fact that an argument or a point was raised by many different people could be quite important to the decision maker. And with that in mind, we started to consider a new approach, which we refer to as debater key point analysis. Specifically in key point analysis, given a large collection of short sentences, these could be arguments or responses to a survey, product reviews, and so on, we automatically generate a bullet-like summary that outlines the most important key points being made in the data, and moreover the relative prevalence of each key point in the data. So you can think of that as a new form of summarization with an important quantitative angle, capable of generating an effective summary of thousands or even tens of thousands of responses in a way that could be quite useful for decision makers. And another important advantage of this approach is that in contrast to other more standard summarization techniques, it comes with a natural form of evaluation in terms of coverage and precision. Specifically, we can use manual annotation over a sample of the data, of the test data, in order to reliably estimate the fraction of responses or arguments that were covered by the identified key points, and also to identify the precision of mapping responses to each key point. And this key point analysis approach was used over the last couple of months to summarize the opinions of thousands of people all over the globe in a series of 3 debates that were broadcasted in Bloomberg TV in collaboration with Intelligence Squared. And you are welcome to take a look at ibm.com/debatable in order to see the full results that we had in these demonstrations, and even try it yourself with the available live demo on that website. So this is all in all a very promising direction of future research in my opinion, and I encourage you to take a look at the first 2 papers describing this by Roy Bar Chaim and colleagues, published this year at ACL and also just now at EMNLP. Okay, so before wrapping up, and after seeing many of the details of how Project Debater works, it is perhaps worth asking why it is really worth pursuing a grand challenge. And the obvious answer is that it helps us to push the boundaries of AI. And as mentioned, over the years, we published more than 50 papers and released many associated datasets to the research community. Interestingly, some of these problems received relatively little attention by the relevant communities. So, for example, the problem of detecting claims or evidence in a massive corpus in the context of a specific controversial topic, although this sounds like a very natural and important problem, it was actually first formulated in the context of a project in the papers by Ran Levy in Calling 2014, and the other paper led by Ruti Rinot in EMNLP 2015, respectively. And similarly, the problems of modeling human dilemma and rebuttal occurred naturally in the context of developing a live debate system, and I'm actually not sure that we were considering these problems otherwise. And finally, of course, we believe that there are many use cases for debating technologies, and we are in the process of propagating some of these technologies into various products of IBM. And finally, we started this tutorial with a few hours ago by mentioning earlier grand challenges. And indeed, the grand challenges in AI were there from day one. Back in the 50s, Arthur Samuel from IBM, the person who actually coined the term machine learning, started to develop the first software that can play checkers at a human level. This sounds obvious today, but back then, when he finally succeeded, it was quite a sensation. Later on, Jerry Tesauro, still on IBM Research, developed the first software to achieve master level play in backgammon. Later on, there was the Blue in chess, and more recently, AlphaGo playing Go, and so on. But I would argue that all these board games lie in what we can refer to as the comfort zone of artificial intelligence. And let me make a few observations to explain that. First of all, when a board game is done, it is easy to know who won the game, and this facilitates the use of reinforcement learning techniques. Second, in board games, moves are well defined and their values can be quantified, enabling the use of game solving techniques. And third, for many such games, massive amounts of relevant structured data were available, for example, in the form of complete games played by humans. And this obviously was imperative to the development of the system. And finally, in a board game, the system may use any tactic to defeat humans, even if human experts cannot fully comprehend it. And we saw that in Go, the system is doing a particular move, and the experts do not really understand. They only understand that perhaps a few moves later when this is too late. So all these four characteristics do not hold for a debate. In a debate, we do not necessarily know who won the debate, and it is even not always clear how to define that. We do not know how to quantify the value of individual moves. We do not have structured debate data at the scale that is required for developing and training an AI system. And finally, it seems implausible to win a debate using tactic or rationale that humans cannot follow. Rather, the system must adjust itself to human rationale in order to even just participate in the debate in a meaningful manner. And therefore, we think that Project Debater is certainly out of the comfort zone of artificial intelligence. It is in a different territory, a territory where humans are actually still better. Humans still prevail, which I think is good news, because it means that we still have many open questions to explore. And by that, let me just end by thanking the truly remarkable Project Debater team at IBM Research, and thank you for your attention and for joining this tutorial.